We will now look at a theorem that relates complex limits to real limits of the real and imaginary part of a complex function. So here we're going to let f of z be a complex function, so we can think about it as a function of x plus iy, whose value is a complex number, and we're going to think about that as being u of xy plus iv of xy, where u and v are real functions of two variables, x and y. We're going to have an input point z0, which is going to be x0 plus iy0, and then an output point w0, which is going to be u0 plus iv0. Then we want to say something about the complex limit as z goes to z0, f of z equaling w0, if and only if the real limit as x and y go to x0, y0 of u of xy equals u0, and the real limit of x and y going to x0 and y0 of v of xy equaling v0. So this relates the complex limit to two real limits of the real functions u of xy and v of xy, which are the real and imaginary parts of my function f of z. So this is an if and only if proof. And so we want to start by proving it in the forward direction. So we're going to assume that the limit as z goes to z0 of f of z is equal to w0. And then we're going to want to write that out using our formal definition of a limit. So we're going to let epsilon be bigger than 0. That'll be an arbitrary positive number. Then we can say there exists a delta greater than 0 such that the modulus, or the length, of f of z minus w0, which we could rewrite as u plus iv minus u0 plus iv0, is less than epsilon for z minus z0. Okay, so the modulus, or the distance between z and z0, which can be written as x plus iy minus x0 plus iy0 less than delta. So essentially this is saying that if z is close enough to z0 and the limit exists, then f of z is close to w0. So now that we've written out the formal definition of what we know because the limit exists, I want to talk about what we want to show here. So we want to show that the limit of x, y going to x0, y0 of u of xy is equal to u0, which is the real part of w0. What does that mean? That means that if the distance of x, y to x0, y0 is small, so that's actually the square root of x minus x0 squared plus y minus y0 squared. If that distance is less than delta, then the distance between u and u0 is less than epsilon. So notice that when I'm talking about the distance between x and y and the point x0, y0, that has to be the two-dimensional Euclidean distance between those points. Whereas when I was talking about the distance between z and z0 in the limit of f of z, then that's actually the modulus, or the complex length. Okay, so that's the first limit that we want to show. We also want to show that the limit as xy goes to x0, y0 of v of xy is equal to v0. Well, what does that mean? That means that if my distance between xy and x0, y0 is small, so again, that's this Euclidean distance. If that is small, say less than delta, then my distance between v and v0, which is just a normal absolute value, is less than epsilon. So what I'm going to do is I'm going to look at these distances, the distance between u and u0 and v and v0. So let's note that the distance between u and u0, or the absolute value, can be written as, or is less than or equal to, the complex distance of u minus u0 plus I v minus v0. So here, what we have on the left is just a straight absolute value, which is the same thing as the modulus of a real number. But what we have on the right is definitely the modulus, or the length, of a complex number. So clearly u minus u0 in length is going to be less than or equal to the length of u minus u0 plus something else, in this case v minus v0. But now I can rearrange those to be u plus iv minus u0 plus iv0. In other words, that's the distance between f of z and w0. In the same way, we can look at v minus v0 and look at that distance as a real number. Okay, and that's going to be less than or equal to the modulus of u minus u0 plus I v minus v0. So here, this quantity and that contribution to the length would be the same, but if I add u minus u0, that would only increase that modulus. Again, we can rewrite that as u plus iv minus u0 plus iv0. So essentially, we can rewrite the distance between u and u0 and v0 as both being less than or equal to the distance between f of z and w0. I also want to note that the distance between z and z0, which is a complex modulus or length, can be written as x plus iy minus x0 plus iy0. But that can just be written as x minus x0 plus I times y minus y0. Now, if I compute the modulus, that would be the square root of x minus x0 squared plus y minus y0 squared. Right? And that's the Euclidean distance of the point xy to the point x0, y0, which came up before here and here. Okay, now that we're putting all of those things together, if we assume that z minus z0, which is the same as that Euclidean distance, x minus x0 squared plus y minus y0 squared, all in a square root, is less than delta, then we have that u minus u0 in absolute value, well, that's less than or equal to f of z minus w0. Okay, that's this line here, which we know is less than epsilon because that is what we assumed at the very beginning here. And v minus v0 is less than or equal to f of z minus w0, which is again less than epsilon. So in essence, what I'm saying is that if z is close to z0, say less than delta, we can show that u is close enough to u0, less than epsilon, and v is close to v0, again, less than epsilon. So that tells us that the real limits of u going to u0 and v going to v0 both exist, which completes the idea of if this is true, then the two real limits are true. So that's one half of the proof. Let's look at the second half. Well, here we get to start with the real limits existing. So we're going to let the limit as x and y go to x0 and y0 of u of xy equal to u0. Well, what does that mean? Well, the formal definition says that given an epsilon greater than 0, so I guess I'm going to quickly add that in. So we're going to let epsilon be greater than 0. So given that epsilon greater than 0, there exists a number delta, but I'm actually going to refer to it as delta 1, and you'll see in a moment, that's bigger than 0, such that if my distance between x and y and x0 and y0, okay, so that's that Euclidean distance between xy and x0, y0, if that distance is less than delta 1, then u minus u0 in absolute value, the distance between u and u0 must be small. And actually, I'm going to make it less than epsilon over 2. So epsilon is arbitrary, so I can figure out a delta 1 that will make it less than epsilon over 2. And that's the definition of the limit of this real function u of xy going to u0 as x and y go to x0 and y0. Okay, so now I'm going to write the second one out as well. So I'm going to let the limit of x and y going to x0 and y0 of v of xy equals v0, and then I'm going to do the same thing. There exists a delta 2 greater than 0. It doesn't have to be the same as the delta from the initial, or from the u limit, such that if the distance between xy and x0, y0, so that's x minus x0 squared plus y minus y0 squared, if that distance is less than delta 2, then the distance between v and v naught, or v0, is also less than epsilon over 2. And you can see, because u and v are different functions, then delta 1 and delta 2 shouldn't have to be the same. Okay? So now we have the definitions of those two real limits. And what do we want to show? We want to show there exists a delta greater than 0 such that if z minus z0, the modulus of that, or the length of that, is small, okay, the distance between z and z0 is small, then we have that the distance of f of z to w0 is less than epsilon, so that is small. Okay, so now we have established that the real limits exist, and now we want to show that that complex limit is indeed w0. Okay. Well, the way I'm going to do this is that I'm going to choose my delta to be the minimum of delta 1 and delta 2. That way, I'm in the situation where if x and y are close to x0 and y0, then I have established that u minus u0 is less than epsilon over 2, and v minus v0 is less than epsilon over 2. Okay, so if I let delta be the minimum of the two delta 1 and delta 2, then I can guarantee that u is close to u0 and v is close to v0. Okay, because both of those inequalities have been satisfied. Okay, so I'm going to do that, and then I'm going to note or I'm going to assume that I'm in the situation where x minus x0 squared plus y minus y0 squared, that's going to be small. So I'm going to assume that xy is close to x0, y0. But let me rewrite those as x, or the length of x minus x0 plus I times y minus y0, or the modulus of that. Okay, because this real distance is in fact equal to the length of the difference between x plus iy and x0 plus iy0, which is in fact the distance between z and z0. Okay, so if x and y are close to x0 and y0, then z has to be close to z0, and so I'm going to let all that be less than delta. So we're in the situation where the real limits, in fact, exist, and u is close to u0 and v is close to v0. So when I look at the distance between f of z and w0, well, that's, in fact, f of z is u plus iv, and w0 is u0 plus iv0. But I can rearrange this as u minus u0 plus I times v minus v0. And I know from the triangle inequality that this is less than or equal to u minus u0 plus I, sorry, no I anymore, plus the length of v minus v0. And because x and y are close to x0 and y0, I've established that the first piece is less than epsilon over 2, and the second piece is also less than epsilon over 2, and that is in fact epsilon. So this concludes saying that if the real limits exist, u going to u0 and v going to v0, then f of z must in fact go to w0. So that kind of concludes our proof. A little celebration square going there. Okay, so the second half of the proof, we showed that if this is true and this is true, right, then the complex limit indeed exists and goes to w0.